Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. Identify the double bonds and check for geometric isomerism at each. Double bond 1, C2 is equal to C3, i.e. CH3-CH is equal to C, Br dash. For geometric isomerism, each carbon of the double bond must have two different groups. C2 has CH3 and H, two different groups. C3 has Br and C4 chain, two different groups. So double bond 1 can show EZ isomerism. Double bond 2, C4 is equal to C5, i.e. C, Br is equal to CH, CH3. For geometric isomerism, C4 has Br and C3 chain, two different groups. C5 has H and CH3, two different groups. So double bond 2 can also show EZ isomerism. Moving on to the next step. Count possible combinations. With two independent double bonds each showing EZ isomerism, theoretically there are 2 times 2 equals 4 combinations E, Z, Z, E, Z, Z. Moving on to the next step. Check for any equivalences due to molecular symmetry. The molecule CH3-CH is equal to C, Br, C, Br is equal to CH, CH3 is symmetric about the C3-C4 bond. Both ends are CH3, CH is equal to and is equal to CH, CH3 with Br on each inner carbon. Due to this symmetry, the E, Z and Z, E combinations are actually identical. One is the mirror image superimposable form of the other through the symmetry axis. Therefore, these two count as only one distinct isomer. And for the final step, final count of distinct geometrical isomers. E, E1 isomer. Z, Z1 isomer. E, Z is equal to Z, E1 isomer. These are the same compound due to molecular symmetry. Total is equal to 3 distinct geometrical isomers. Why other options fail? A. 2 undercounts ignores the mixed EZ isomer. C. 4 overcounts does not account for the molecular symmetry that makes E, Z and Z, E identical. D. 6 greatly overcounts, no basis for 6 isomers here. Therefore, the correct answer is B. Therefore, the correct answer is option B.